So for page 5, we're starting with a couple of equations at the top here, this one here, this one here, that actually come from physics. And I want to go through what is in these two equations. So first you have c, the speed of light, and it's a constant right here in meters per second. It's 3.00 times 10 to the 8th meters per second, which is crazy fast, of course. That little lambda, the thing that looks like an upside down Y, that's wavelength. It's how long your wave is. And the classic way to look at this is to think about a traditional sine wave that goes up and then down and then up and down and up and so on. One wavelength is how much distance is it between repetitions. So from here, and notice it goes up, down, and then here. That distance is the wavelength. And you don't really need to know my drawing here very much. That's more of a physics thing, but it gives you something visually to think about. That V actually isn't a V right here. It's here and here. It's the same thing. It's actually a Greek nu, but for our purposes, we don't need the Greek. Let's just call it V. It's what's known as frequency. And frequency is how many cycles happen per second. So for example, one cycle is right here, from here to there. That's one cycle. So if I do this, beep, 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 it's happening about once a second. And so you would say the frequency is about 1 or 1 hertz. You'll see the unit is per second. And by the way, that's not a 1 second, that is per second. Or sometimes it's called hertz. Now let's go a little faster. Beep, 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 beep. Okay, that was faster. That's more like 2 hertz, 2 cycles per second. It might have even been more like 3 cycles per second. That's what frequency is. It's how often something happens per second. All right, on the other equation, E is energy, right here, in joules or kilojoules or something like that. It's the same V. And H, this H right here, is called Planck's constant, right there. And you might have actually heard about Planck's constant in a very odd way recently. It came up in the show Stranger Things. I don't remember the scene exactly. It was something like they needed a code to get through a locked door or something like that. And somehow they knew the code was Planck's constant, but they didn't know what it is. I don't know it either. I don't have it memorized. And they knew that there was this girl that knew it. And so they contacted her through the one kid with the curly hair. And I remember there was something where they had to sing the Never Ending Story song so that she would tell them. And it was a pretty funny scene. But anyway, that was Planck's constant. And so if you watch Stranger Things, you might remember hearing that. And so that's what that is, and that's a constant. Now, what you'll often see is you'll be given a problem where they give you enough stuff, like they'll give you the speed of light and the wavelength, and you have to solve for the frequency, and then you use the frequency in this other equation. So you'll see problems where you have to use both equations in the same problem. And we'll see those later. Okay, on to the Bohr atom. All right, we talked about this in the homework already, in that you have special orbits and the electrons reside in them. Last year, you were told what the energy values of the orbits are. So for example, you were told that this first orbit has a certain energy, and maybe it was in joules. And then you were told the second orbit has a different energy in joules, and the third orbit has a different energy in joules. You were given these last year. This year, I'm going to have you calculate it, and it's really easy. What you do is you take either this number or this number, just one is in kilocalories, the other one is in kilojoules, and you divide by the orbit or shell squared. So take a look at this example here, this first one. It says calculate the energy. It says kcals, so I'm going to use this one, in moving 1 mole of electrons from level 4 to level 2. Well, when you do a problem like this, you have to do final minus initial. And so final is going to be the second level. And so to find the energy for that, you take the 313.6 and divide it by 2 squared, which is the level. And that will give you this negative 78.40. Then minus here. The fourth, you do the same thing. You take the negative 313.6 and divide by 4 squared, and that will give you negative 19.6. And you do the math and you get the answer as negative 58.80 kcals. And notice, this is for a mole of electrons. If a problem were to ask for a single solitary electron, you would just divide this by Avogadro's number. And that would give you whatever the energy is for one electron. Moving along. Okay. Up here, this is just talking about when you have electrons jumping around within a D subshell, that often gives off colors of light that we recognize. Whereas when they jump around within S and P subshells, that usually is not what we see as light, and that's a much higher energy thing. And that leads us to the spectrum of light, and the fancy word for this is the electromagnetic spectrum. And it shows light right here in the middle, and then it was expanded. And then it shows lower energy things like infrared, microwave, and radio waves. And then to the left, it shows higher energy things like ultraviolet, X-rays, and gamma rays. Now be aware, sometimes you'll see this chart in its reverse order. So sometimes you'll see an author will put gamma rays on the right over here and radio waves on the left. So be aware, if they reverse it, of course, the energy direction reverses and high energy would be on the other side. Now, what's interesting here is that these things like microwaves and radio waves, they're the same things as light. We just don't see them. Our eyes are tuned to this very narrow section right here. And our eyes, we just don't tune into microwaves. If our eyes did tune into microwaves, every time you use a microwave, which uses microwaves, hence the name, you would actually see it in there. That'd be pretty confusing. All right, let's take a look at this problem. Which salt gives off more energy? Well, it says that this is blue, and this is orange. And just to be confusing, I'm using green. So you look on the chart. Blue is here. Orange is here. High energy is on the left. Energy increases this way. So blue is higher energy right here. So that's why the CuCl2 is the higher energy situation. And down here, this is talking about how depending on what type of energy is being pushed onto molecules, they can move in different ways. And so low energy here, this microwave radiation, that causes molecules to rotate. In other words, they just kind of spin around a little. A little bit higher infrared, that now gets them vibrating and shaking around. And you mainly know that as temperature. So if you take a molecule like a water molecule, its motion, it's spinning around and it's shaking and all that, that's what temperature is. The more shaking, the higher the temperature. And then ultraviolet, which is higher energy and visible, that actually is where you start to get electrons jumping from one level to another level. So that's where you start getting the Bohr atom situation, where you have electrons jumping from the first level to the third, and so on. Okay. Oops. I just want to move, not spin. Okay. That's fine. And then let's zoom in on that. Okay. Down here, this Coulomb's law section here, oh boy, we're in a weird place here. Yes. And just zoom in on that. Oh, forget this. Let's start this over. See, what's happening here is my computer knows that I'm recording this, and so it's making things difficult on me. We'll start with a brand new page, because that other one was clearly getting upset. Okay, right there is good. This section that says Coulomb's law, you kind of know this already, and what you know this is opposites attract and similar charges repel, and this helps us explain why one scenario has a greater attraction or a weaker attraction. So I'll give you an example. Let's say we took a proton and an electron. They would, of course, attract. They would be attracted to each other because they're opposite charges. If you take an electron and another electron, they, of course, would repel. Now, where Coulomb's law comes in is it helps to explain, well, what if I had 3 protons? If I had 3 protons attracted to an electron, this electron would have a stronger attraction to 3 protons, and that's where Coulomb's law comes in. Let me give you an example with some ions. Let's say we took sodium and chlorine ions versus calcium and oxygen. Sodium and chlorine are attracted, calcium and oxygen are attracted, but the calcium-oxygen pair has a stronger attraction because it has greater charge, the +2 and the -2. And the way you might see this is I might ask you, hey, sodium and chlorine ions are attracted to each other, calcium and oxygen are attracted to each other, and the calcium-oxygen combo is a stronger attraction. Why? Well, a good explanation would be for you to say, well, calcium is a +2 charge, oxygen's a -2, and that is a higher charge than +1 and -1 in sodium and chlorine ions. This higher charge in the calcium and the oxygen, according to Coulomb's law, will have a stronger attraction. And that's where you can use something like this. By referencing Coulomb's law, it gives your statement a lot of strength. And we'll practice this over the next couple weeks. I'll go through how to give really good explanations. And so Coulomb's law says there's two things that cause greater attraction or repulsion. A higher charge, which I just showed with the calcium oxygen versus sodium chloride, and also if they're closer. So if they're just physically closer. So if you have a proton here and an electron here, that is going to be a stronger attraction than a proton here and an electron here. This is a mathematical proportion that explains it. You don't really need it. We use this in physics, but in this class, we're never going to actually calculate anything with it. You're just going to use it to help explain a phenomenon that we are observing. And last thing today, will just get us started with electron configurations. I said to write the electron configuration for lead, which unfortunately has 82 electrons. So I was lazy, and I just started in the 6 shell to save time. And hopefully you follow this, 6s2, 4f14, 5d10, and 6p2.